All right, so let's finish up this week here. We've been talking about solutions and solution reaction. Today we're going to learn how to quantitatively deal with solutions. But first we're going to paint a little bit more of a picture about what a solution composition looks like here. Okay? So it turns out that depending on whether you have an ionic compound or a covalent compound, these will behave differently when you put them into solution, when you take them and you dissolve them in water. Okay? So what I have here is two beakers, and I'm going to fill these beakers up with water. All right, and we're going to dissolve an ionic compound in one of them and a covalent compound in the other one. For our ionic compound, we're just going to use as an example here NaCl. And I'm going to picture my sodium molecule, my sodium atoms rather, in orange and my chloride ions in green. All right, so in orange here, I have these positively charged sodium ions. And in green, I have these negatively charged chloride ions. Okay, so if we take this solid sodium chloride and we place it into water, what we're going to see is that these two ions will dissociate from one another and they start floating around independently. So they're no longer bound together. They are now separated out when we put this compound in solution. Okay, so what we say is that ionic compounds dissociate which is a fancy way of saying break up or break apart in solution. Okay, so these sodium ions and these chloride ions, at first they're stuck to one another, but they're bound together. When you take an ionic compound and you put it into solution, it actually breaks apart into these two constituent ions here. So now the positive ions are floating around separately from the negatively charged ions. If we take a covalent compound, we'll pick something simple here, carbon monoxide. I'm going to picture my carbon molecules, my carbon atoms in black, and my oxygen atoms in red here. If we take a covalent compound and we make a solution with it, there's a big difference here than what we see for our ionic compounds. Covalent compounds do not dissociate in solution. So I'm just going to see my compound floating around with my carbons and my oxygens still bound together. All right, so we would say covalent compounds do not dissociate in solution. That carbon-oxygen bond is not broken for a covalent compound, unlike my ionic compound, where now those two ions are floating around independently of one another. Okay? All right, so last time we spent a lot of time talking about these precipitation reactions, predicting our products for our precipitation reactions, which are these double displacement reactions. We need to do this swap method here. All right, so let's take a look at an example, and then we're going to tie it back into this picture that we just painted here. We're going to take sodium chloride, a solution of sodium chloride, and we're going to combine it with a solution of cesium bromide. Okay, and I want everybody to take a second and predict the products of this reaction by swapping our cations here. All right, so when we pair our sodium with our bromine, sodium, is Na+1. Bromide is Br-1, so that would be NaBr. And then we're going to do the other side. Cesium is +1 and chloride is -1, so that would be CsCl. Remember to get your formulas, you need to make sure to look at those charges. And then in order to get the state of matter of these compounds, where are we going to look? That's solubility tables. So let's take our two compounds here. NaBr, CsCl. Okay, so we need to look up NaBr and CsCl. Okay, we need to determine whether these are insoluble or soluble, whether they're going to be aqueous or solid in our balanced chemical equation. Okay, so take a second to look these up. Okay, if I find my bromine on my table here, my bromide rather, this tells me that bromides are insoluble except when paired with silver, mercury, or lead. I don't have silver, mercury, or lead, so this one would be soluble. And what about my cesium chloride? Same thing. If I look up chlorine on my table, chloride on my table here, I see that chlorides are soluble unless they're paired with those same silver, mercury, or lead. So this is also soluble, which means that both of them are going to get what sort of state of matter designation here? They're both going to be aqueous. All right, so from a picture standpoint here, we took these two beakers, one with sodium ions and chloride ions. The other one had cesium ions and bromide ions, and we mixed them together here. But we didn't form any sort of a solid compound. Now we just have a mixture of chloride ions floating around, sodium ions floating around, cesium ions floating around, and bromide ions floating around. There's no new bonds that have formed. All we've done is taken two solutions and mix them together. We have no solid product that's formed here. So if both of your products are aqueous, we say that no reaction has occurred. All right? So what I would do here, if I looked up both of these and I saw that both of them were aqueous, I would simply say no reaction, or we get lazy and we put NR for no reaction. All right? So for my balanced chemical equation here, rather than including these two products, again, there's no chemical reaction that occurs. How you would finish off this chemical equation is by saying NR. No reaction has occurred. All you've done is mix two solutions together. There's no solid product that is formed. Okay, so we can just say, kind of lay it out more clearly here. If both products are aqueous, no precipitation reaction has occurred. Whoops. All right, so no reaction. We would write NR. All right, all you've done is take two solutions and mix them together. You haven't actually created any new product. You haven't formed any new chemical bonds because no solid has been produced in that reaction. Okay, so we've talked about these reactions qualitatively, meaning that, like, given these two components, we know how to do our swap method of these cations and predict our products of this reaction. Okay, now we're going to learn how to quantitatively talk about solutions. Quantitatively, how we talk about solids is we use our balances in the lab. We use grams. We mass out a certain amount of a particular solid for a chemical reaction. For solutions, we use something called concentration. Okay, concentration is a quantitative measure, a number that tells you how much of a compound is dissolved in a solution. Okay? Our units for concentration are what are called molarity. We use the symbol capital M for molarity. Okay? And molarity stands for moles over liters. All right, that big M is a shorthand representation for moles per liter. So if I, for example, a solution of NaCl has a concentration of 4.5 big M. All right, that's the concentration of this solution. It's telling me how much sodium chloride there is dissolved in that water. And what this 4.5 big M is telling me is that there are 4.5 moles of NaCl in 1 liter of that solution. Okay? Concentrations are not unlike molar masses. Molar masses were allowing us to jump from grams to moles or moles to grams. Our concentration is going to play a very similar role, except for we're going to be jumping between which two units? Moles and liters. Right? When we have a solution, we don't go to the balance and pour it onto the balance. That wouldn't work out too well. It's a liquid, right? No. We go to a graduated cylinder and we measure out a specific volume of that substance. And then we need to know how many moles of crap we got floating around in there. How much sodium chloride did I just pour into that graduated cylinder? We're going to use our concentration, our molarity here, as a conversion factor that's going to help us jump from moles to liters. Okay? So the first step in these problems here is going to be to take this concentration information, the big M, and convert it into something that we can use in our math. We got to split those units back up. That big M stands for moles per liter, and so that's what we're going to do. We're going to take that number, 4.5 big M, and we're going to split it up so that it's 4.5 moles of sodium chloride in 1 liter. All right, so then let's do an actual problem here using our concentration. How many moles of potassium bromide are in a 2.7 molar solution with a volume of 1.6 liters? Right, so I went to my graduated cylinder. This is one of those massive graduated cylinders. I poured out 1.6 liters of this 2.7 molar solution, and now I have to know how many moles of my potassium bromide are actually floating around in that graduated cylinder. So step one, everybody's going to take a second and they're going to turn this 2.7 big M into something that we can use in our math by splitting up those two units. All right, again, that big M stands for moles over liters, so that's exactly what you're going to do. You're going to split it back up, just like we did grams per mole when we were using our molar masses. We turned it into something that we can use in our math. Same thing. So this becomes 2.7 moles of KBr are in 1 liter of my solution. All right, and again, this is going to play the role of a conversion factor. Just like we converted between inches and centimeters, this is going to allow us to convert from liters to moles. So I'm going to start my problem here. I need to know my number of moles that are in 1.6 liters. So I have 1.6 liters of my solution. I'm going to take this concentration here, and am I going to use it as is, or am I going to be able, or am I going to flip it? I need my units to cancel out, right? So I need liters on the bottom and moles on the top. And let's just notice, just like all of the other math that we've been doing, if we set it up correctly, our units will cancel out in such a way that we're left with units of moles, right? This concentration here is just another conversion factor that we're learning. All right, so 1.6 times my 2.7, I get 4.32. And what are my units? right? Liters have canceled out, so I'm left with moles of KBr. So again, just paying attention to our units lets us know that we're set up correctly. All right, the last step though, pain in the butt, chemistry, math, what do we got to do last? Sig figs, awesome. So both your volume and your concentration. Concentrations are not exact. They are measured values. So you will have to pay attention to both when figuring out what your sig figs are. In this case, they both match. They both have 2. So I'm going to make sure to round my final answer here to 4.3 moles. All right, so concentration. This is how we talk quantitatively about how much of a compound that we have in solution. I will tell you, this is a very popular, solution chemistry is super popular. I was a biochemist. That's what my PhD was. Every single chemical reaction I ever carried out, ever in the lab, took place in solution. Solutions are a really popular medium for chemical reactions to take place because crap's all floating around. They can come in contact with one another, right? If you put 2 solids together, there's not much chemistry that can happen between those 2 solids. In solution, everything's floating around. There's a lot more collisions. A lot of chemical reactions occur in solution. So solutions are a very, very popular medium in which chemical reactions take place here. Okay, so we're going to use this same concept here. We're going to play another game here, and I want you guys to see if you can do this one on your own. What volume, we'll say in liters, of a 2.85 molar solution of silver nitrate contains 4.6 moles of silver nitrate. All right. I want to see if you guys can figure this one out on your own here based on what we've been doing thus far in the course. Again, your first step, you got to take that 2.85 big M. That's not how we use it in our math. How we're going to use it in our math is we got to split it up. We got to split up those units. All right, that's step 1, and then you can go and set up your math problem. Okay, so step 1, I took that concentration, that 2.85 big M. That's how it's going to be written in our problem. That's how we represent concentrations. But to use it in my math, to make sure I've set up my problem correctly, I'm going to break it up into moles over liters, right? So now it's 2.85 moles over 1 liter of solution. Okay, my problem's starting me off with the 4.6 moles of the silver nitrate. So then I'm just going to multiply by that concentration, right? Just like we did last time. What's the problem here? My units don't cancel out, right? Again, all about the units, making sure it's set up correctly. This is moles times moles divided by liters. Nothing cancels out here. So instead, how am I going to use that concentration? I got to flip it, right? So instead, I'm going to divide by my molarity here, divide by my concentration. So the 2.85 moles of silver nitrate are on the bottom, and my liters of solution, my volume, are on top. All right, now moles will cancel out, and I'll be left with units of volume. So if I needed 4.6 moles of this silver nitrate, then I would have to go to my graduated cylinder and measure out 1.614, blah, 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 but then to the correct number of sig figs. Actually, real quick, correct number of sig figs would be, right? So this number has 2, this number has 3, so we got to go with what's fewer here, so my 1.6 liters. Right, so in my experiment, I really need to get this 4.6 moles of silver nitrate. I got to go to my graduated cylinder and measure out 1.6 liters of that solution. Okay, so this concentration and volume, that's how we quantitatively talk about a solution. Right, for solids, it was a mass and a molar mass. That's how we jump to moles. Right. For solutions, it's going to be a volume and a concentration. That's how we relate to moles. And of course, we need to get to moles because that's how we talk about chemical reactions, right? That's how we use our balanced chemical equation. Okay, so let's roll this all in together, what we've done. All right, so step 1, let's just get our balanced chemical equation for these precipitation reactions, okay? We'll write down the whole problem here. So let's do strontium chloride. Okay, step 1, we need to write a balanced chemical equation. All right, a solution of strontium chloride. So strontium chloride aqueous is mixed with aqueous K2SO4, potassium nitrate. And we should be able to predict the products of these precipitation reactions. All right, so I'm going to go ahead and just copy this because what we are going to need, of course, is our constants page here. So just to have this up on the screen. What am I pairing the strontium with on my product side? The SO4, okay. So SR and SO4. In order to put these formulas together, I need to know the charges of these two ions. So what is the charge of the strontium ion? Yeah, based on my periodic table in that second column there, it's +2. And the sulfate ion is one we just got to know. What's the charge of the sulfate ion? -2. And now, if we forget, we have our little solubility table cheat sheet here that has all of our polyatomic ions, right? So we shouldn't have any excuse for not knowing that sulfate is -2. So when we put this strontium and this sulfate together, what's our chemical formula going to be? SrSO4, right? We play the swap game, but then we got to fully reduce our formula here. Okay, so now I'm going to put the potassium with the chloride. Oops. Whoa. All right, so let me move this over. Again, I know potassium is going to be paired with chlorine. But again, in order to get my formulas, I'm not going to say K2Cl2, right? Even though there's a 2 over here on both of these. That's not how we get our chemical formulas. Now, let's not forget what we did at the very beginning of the semester, right? We will account for those little 2's when we balance our chemical equation. When it comes to building our chemical formulas, it's all about the charges. The only thing I'm going to pay attention to get this formula are the charges of the potassium and the chlorine. So this is the most common mistake people make, is they just kind of copy and paste from one side to the other. That's not going to get you, it might work out, but it's not going to be guaranteed, right? So this is not how we do this here. Instead, we got to look at the charges of each of these ions. Potassium's +1 and chloride is -1. So my formula for for potassium chloride is just KCl. I was about to say my formula for KCl is. Okay, so I have these little 2's here, right? I will account for that when I balance my chemical equation. When I balance my chemical equation, I'm going to include a coefficient of 2 out front here. That's how I'm going to make sure I have the same number of potassiums and chlorines on each side, right? So 2 different steps that you don't want to conflate here. One is building your chemical formulas, all about the charges, exactly what we learned how to do at the beginning of the semester before we even talked about chemical reactions, right? Then once you have your chemical formulas, then you can balance your chemical equation. But this isn't done yet. I need the states of matter here, so I'm going to look up each of these compounds, my strontium sulfate and my potassium chloride, on this table here, on my constants page, my solubility table. And I got to figure out which one's soluble and which one's insoluble, all right? Because I got to know which one's going to get the S and which one's going to get the AQ in my formula, or in my chemical equation. All right, so for this first one, I'm going to look up my anion, the sulfate ion. And this tells me that most sulfates are actually soluble, but there are a few exceptions, and that is when it's paired with silver, mercury, lead, calcium, and strontium, right? So this would be an insoluble exception. This is an insoluble compound. If I look up my potassium chloride, I find my chloride on my table. Whoops. And this says that most chlorides are soluble unless it's paired with silver, mercury, or lead. And this isn't silver, mercury, or lead, right? So this would be an example of a soluble compound. So then if I'm going to finish my balanced chemical equation here, I have my strontium sulfate with the S because it's a solid, and I have my 2 potassium chlorides with the AQ because it's aqueous. Okay? So step 1, we need our balanced chemical equation so we can work with it quantitatively. All right, and now we're going to roll together what we learned how to do with stoichiometry to now what we just learned about solutions and concentrations here. So I'm going to tell you that in this reaction, a 1.5 liters of 2.6 molar solution of the strontium chloride is consumed. So I have this solution of strontium chloride that has a concentration of 2.6 molar, and 1.5 liters of that solution were used up in the reaction. And what I want to know is how much solid is produced in this chemical reaction. So what solid am I talking about here? My solid strontium sulfate. So this problem here is starting me off with an amount of my strontium chloride, but it's asking me for an amount of strontium sulfate. And how do we jump from one thing to another in our balanced chemical equation? What do we need? A stoichiometric ratio. Okay, so before I even do any other math, I know I'm going to need a stoichiometric ratio that connects these two compounds here. Right, my solid strontium sulfate and my reactant, the strontium chloride. So 1 mole SrCl2 over 1 mole SrSO4, or we can flip it. Okay? Anytime you are working with a chemical reaction, you will need to convert to units of moles. We always say, when in doubt, go to moles. You don't know what you're doing in a problem. You read the problem, you're like, oh crap, I got no idea what's going on. When in doubt, go to moles, because chemists love moles. That's how we talk about chemical reactions. In order to use this balanced chemical equation, you have to be in units of moles. Right? I know just because of my question is giving me one component in my chemical equation and asking me for another, I know somewhere in my math is going to have to be one of these stoichiometric ratios here. That's the only way we can talk mathematically about chemical reactions. Okay? So now I'm not given moles of the strontium chloride. I'm not even given grams of the strontium chloride. Instead, I'm given this new quantity that we've talked about, a concentration and a volume. And I need to get it to moles so I can use one of these stoichiometric ratios. So based on what we just discussed about concentration, see if you can get me to moles of strontium chloride so we can use one of these stoichiometric ratios. Okay, so again, that 2.6 big M, in order to use it in my math, I'm going to break it up into moles over liters. And then I'm going to use it as a conversion factor that would allow me to jump from liters to moles. It would also do moles to liters, but in this case, I'm already starting out with 1.5 liters. And I need to get to moles of strontium chloride using that concentration. Okay, and if I stopped here, what would my units be for my math? Moles of strontium chloride, but that's not what it's asking me for, right? It's asking me for moles of solid. So I need to make one more jump here to get to moles of solid using that mole ratio. All right, so again, every stoichiometry problem will be using a mole ratio. In this case, it's just 1:1, but I can see units-wise that everything's set up correctly. All right, punch this into my calculator. I get 3.9. If I'm looking at my units, liters cancel out, moles of strontium chloride cancel out, and so I'm left with that moles of solid product, my strontium sulfate. And then the last step is sig figs. In this case, my calculator did just fine. My final answer here would be my 3.9 moles of solid. Okay, so what we learned how to do is to talk quantitatively about solutions using these concentrations. And we're going to plug that into what we already know about stoichiometry, because our concentrations are just another way to jump into units of moles, right? And once we're in units of moles, we can use our balanced chemical equation to, for example, predict how much product is formed in a reaction. All right. For the sake of time, I'm going to give you another balanced chemical equation here, and you're going to do another solution stoichiometry problem for me. All right. So if you mix sodium chloride with lead nitrate, you'll get solid lead chloride and aqueous sodium nitrate. Okay, so here's a balanced chemical equation. For the sake of time, I balanced it. So if 0.75 liters of 2.3 molar NaCl is consumed, how many moles of solid are produced? Okay, so I'm going to give you guys a head start. I'm going to quietly kind of fill in the work, and then we'll go over it at the very end of class here. Let's see. All right, so I'm going to use my volume and my concentration. If I stopped right here, I would have moles of sodium chloride. But my problem is asking me to jump from one part of my balanced chemical equation to another, so I'm going to need to use that stoichiometric ratio that says that there are 2 moles of sodium chloride consumed for every 1 mole of lead chloride that's produced, lead 2 chloride that's produced. All right, so now my problem's set up so that liters cancel out, moles of sodium chloride cancel out, and I'm left with moles of lead chloride. If I punch this into my calculator, I get 0.8625. Again, my units of moles of PbCl2. And then finally my sig figs. Remember that mole ratios are exact, so they do not limit your number of sig figs. So I'm limited to 2 sig figs here, 0.86 moles of solid product. All right, so our concentration is how we quantitatively talk about solutions, and we can plug that right into what we know about stoichiometry because it's just another way to convert to moles. Cool.